Hello guys, on the first part of this lecture, at the end of it, we discussed our strategy to calculate the density of states as a function of k, so rho of k, which was to use part of a sphere defined in the k space, the sphere with radius k. So this would look something like this. You know, in k space you have the three axes, kx, ky, and kz, and we're able to define a sphere with radius k, so we drew only the first octant, which looked something like this. The whole surface of the sphere would have 8 parts like the ones we're drawing, and the radius of this octant is k. So this radius right here is k. So the set of all points with magnitude of wave vector equals to k lie on the surface of this sphere, this octant in our case. So we will use this sphere, and particularly the volume of the region defined between the surface of this sphere and another sphere with points on the surface with radius k plus dk. So I'm going to draw this other octant here in purple, but it has a slightly larger radius, k plus dk, right? In such a way that this radius here, the outer radius, is k plus dk, and you have a shell volume defined between the two surfaces. So the shell has the thickness equal to dk, and it's actually a solid, a volume, it's not a surface. Between the inner sphere in green and the outer sphere in purple, you have an actual solid that occupies a volume in the k space, okay? So the space within this volume has all the points corresponding to wave vectors with magnitude between k and k plus dk. So this has to, geometrically, this has to make sense. So we're going to count the number of points with wave vector between k and k plus dk. By doing this, we're able to count these points, and as we said, they're the points in between the sphere with radius k and the sphere with radius k plus dk. All the points within the range or within the solid defined by the region in between these two spheres. The solution we're considering corresponds to standing waves, in the sense that the psi function, or the wave function, we said was the product of a periodic function, okay, and a term that corresponds to a standing wave and looks like this: minus j times k dot r. But we argued that for each wave propagating in the forward direction, there was going to be a wave propagating in the reverse direction, minus k, so that it could be written like this: e to the power of positive sign j times k dot r. And if you use Euler's identity, this would give us the following: uk times 2 cosine of k dot r, okay, which corresponds to standing wave. So the standing wave is made up or composed of waves, plane waves, with wave vectors k and minus k in opposite directions. So for this reason, we needed to consider only the portion of the sphere associated with the positive k values, because the negative k values are automatically taken care of, since the solution is the superposition of the two, okay? And as we saw, this portion is 1/8 of the sphere, which is called an octant, okay? So we're just recalling what we just discussed. So you would have an entire sphere, which I'm going to attempt to draw here, maybe, right, which would look something like this. And if you divide this sphere in 8, you're going to get only the first octant here, which corresponds to positive kx, ky, and kz value. So we can find the volume of this octant from the area of the surface of the sphere. Okay, so we know that the surface of the sphere, the surface area is equal to 4 pi times r squared, where r is the radius. Now, since we're considering only one octant, we need to multiply this by 1/8, so we get 1/2 of pi times r squared. Since we're on the k plane, r is equal to k, so 1/2 times pi times k squared. Now, to get the volume, we can multiply this by the thickness dk. So it's like you have the inner surface. Okay, so let's say kx, ky, and kz, and you have the inner surface of the first octant with radius k, and then the surface with radius k plus dk right here, both in purple in this case. And if you take the surface of the inner octant, the inner surface, and multiply this by the thickness dk, okay, considering that dk is, differential, the inner surface and the outer surface areas are almost identical, not identical. So if you multiply dk by the surface of the inner sphere, you get the volume of the shell. So that's what we did here. Okay, so 1/2 times pi times k squared is the surface of the inner sphere. You multiply that by dk and you get the volume of the shell. Since each k can be associated with electron with two possible spin states, positive spin and negative spin, we need to consider twice the volume calculated just before. Okay, so this only means that we need to multiply this result by 2 in order to take into account the two possible spin states. Okay, so and now finally dividing the volume of the octant that we just calculated, multiplied by 2 of course, dividing this by the volume occupied by one single space, we find the number of states. Okay, so the idea is that the number of states with wave vectors between k and k plus dk is going to be twice the volume of the octant. So I'm going to draw the octant here. I'm talking about the volumetric region, of course, because the idea is that inside this volume in k space you will have all of the points associated with the states with wave vectors within this range between k and k plus dk. So if we divide twice this volume by the volume occupied by one single state alone, okay, so you can think of a cuboid in which at the center you have one single k value. So the volume of the k value is the volume cuboid. Now if you divide twice the volume of this region, which has all the states, by the volume of each individual state, you will get an estimate of the amount of states or the amount of points that fit within this region, multiplied by 2, of course. So now we just need to substitute the expressions, right? The volume of the octant is, as we just said, 1/2 times pi times k squared dk. And we calculated before the volume of each state, which was pi cubed divided by Lx times Ly times Lz, which, as we said, is the volume of the actual block of semiconductor that we are taking into account in physical space, right? So let's say this is silicon, and we're considering a chip with dimensions Lx times Ly times Lz, something like that. And if you do the calculations, well, this can be cancelled with this. K squared does not cancel with anything. Pi cancels with pi cubed to give pi squared in the denominator. This is V, right? This guy right here is the volume V. So this will turn out to be V times K squared dk divided by what remained in the denominator, which is pi squared. Pi squared. That's the number of states. This is the actual number of states within the range k and k plus dk. So there, that's the result. Where, as we said, V is the volume of the solid, the block of semiconductor, which is Lx times Ly times Lz. And, well, by definition, we said that rho k dk is the number of available states between k and k plus dk, or in other words, with wave vectors between k and k plus dk per unit volume of the material. So all of the quantities, be it rho of E or rho of K, the carrier concentration, and all of these things related to the amount of carriers or the number of states are normalized with respect to volume. Okay, so usually given in quantities per centimeter cubed, which means that they're quantities per unit volume. So you need to divide this by the volume to normalize it. So this is convenient because this means that this quantity right here is going to be equal to what we've just calculated if we divide it by the volume V. Okay, so this is equal to this if you divide by V, which cancels with the D, the numerator. Okay, you have to divide here as well, divided by V, which means that rho of K dk is equal to K squared divided by pi squared times dk, which is a much simpler expression, right? So that's it. This is rho of k dk, okay, right here. So if we divide by v, we arrive at the simple expression for rho of k dk. And by comparison, since both sides are multiplied by dk, the density of states as a function of k, rho of k is simply k squared divided by pi squared, which is even simpler, as you can see. So this expression gives the density of states as a function of k. This is what we sought out from the beginning, okay? But we saw that the electron can assume only certain discrete values of k, which is associated with the momentum of the electron. Since there's a linear relation between the wave vector k and momentum p, the direction of k is the direction of motion associated with the electron inside the solid. So the direction of this vector is the direction that the electron is generally moving. The magnitude of k is proportional to the electron's velocity as a consequence, because, well, momentum is, in classical mechanics, m times v. So therefore, if there's a linear relation with this with respect to momentum, then k varies in proportion to v. Okay, the larger the k, the larger the velocity or the speed of the electron. What we just calculated is the density of states, which is related to the amount of electrons that have a given k. So we got the expression rho of k is equal to k squared divided by pi squared. So as you can see, if this is the density of states or the amount of electrons per unit k, it is not constant with respect to k. So this varies with k. This is an important fact. Electrons with different wave vectors and therefore with different velocities are going to happen in different numbers. You're going to have different amounts or different densities of electrons with the different momentums. Since from the definition rho k dk is the number of electrons which have wave vectors ranging from k to k plus dk, in other words, rho of k is the number of electrons per unit k, per unit volume as well. Because of this, the number of electrons per unit k is not constant. It is actually proportional to the square of the wave vector k, the magnitude of the wave vector k. So as you increase k, the number of electrons per unit k increases. And this is an important information right here, because if you draw the band structure, E is a function of k, with the conduction band and the valence band, this means that the density of states are not homogeneously distributed along these bands. In fact, for smaller values of K, you're going to have smaller density of states or number of electrons per unit K in the case of the conduction band. So you're going to have less states, smaller density of states. And as K increases, okay, so think of these points right here, the negative values, we can only think of the positive values. So as K increases in this direction, so does the density of states rho of K. So that means that you have more states per unit K. The states are going to be bunched up together. You're going to have more states as you go up in the bands. Okay? The same thing will happen in the valence band in the opposite direction. So as you are closer to the smaller K's right at the band edge here, you'll have smaller density of states, and as you go into the band, you will have more states, and the states are closer and closer together. And this is mathematically given by this expression right here. Okay, this is what gives us this information. So close to the band edge, you have smaller density of states. In fact, for K equals 0, this would be exactly equal to 0. And as K increases, right, the magnitude of K increases, the density of states, I'm drawing here, these lines correspond to the states, right? The density of states per unit K increases, so you have more states per unit K. So in the valence and conduction band, this density grows from the border or from the band edge towards the center of the band. When I say the center of the band, think of the energy bands or the band diagrams like we usually draw it, you know, like this. So this is the conduction band, and this is the, let's say, the valence band, and the band edge, and of course this is energy, and the band edge is right here for the conduction band and right here for the valence band. So edge, and the center of the band is right here, right? In the bulk of the band, right here for the valence band. So when we're saying that the density of states increase from the band edge towards the center of the band, we mean exactly what we drew right here, right? Towards the band edge, you have smaller density of states. As you go towards the center of the band, as you go up in the conduction band and down in the valence band, you will have larger densities of states. So as you move towards the center of the bands, there are more states available. Okay guys, so this was it for today. We discussed the density of states as a function of K in today's lecture. On our next lecture, we're going to talk about the density of states as a function of energy E, and we're going to derive this based on the expressions that we have looked at today. So thanks very much for your attention, and I'll see you around.